let's start talking about what we can actually do with these derivatives. And what we're going to talk about for the rest of this video is marginal analysis. And what marginal analysis is it's using derivatives to figure out some different quantities about profit, revenue, and cost. In economics, these three functions are used to describe your businesses mathematically. So C of X is the total cost to produce and sell X units. R of X is the revenue from selling X units. And P of X is the profit from selling X units. Instead of referring to things like F of X and G of X, when we're dealing with the context of cost, revenue, and profit, we use capital C, capital R, or capital P. So let's start with cost functions. Cost functions typically have two parts, fixed costs and variable costs. And for the most part, we're going to deal with linear cost functions. So our total cost is going to consist of our variable costs. Those are the costs that change as we increase production, plus the fixed costs. Those are the costs that don't change as we increase production. Fixed costs are things like the cost of insurance or the cost to keep a night watchman at your plant. Those things, even if you're not producing anything, you're still going to have insurance, and you're still going to have your night watchman. These things might also include design for a product, tooling the factory, or training your workforce. Your variable costs increase as your production increases. That's why they're called variable, because they change. And the things that might include in there are materials, packaging, and shipping, because these are all can be included in the cost per item in our variable costs. Suppose the cost of producing X items is given by a function C of X equals 5X plus 1,000. Let's go ahead and find C of 0. What this means, when I find C of 0, that means in place of X, I'm going to go ahead and put 0. 5 times 0 plus 1,000 equals 1,000. Now what this is this is my fixed cost, because remember, fixed costs are costs we incur even when we don't have any production, and when we put 0 in, we're saying there's no production. So this second term back here, the 1,000, that's our fixed costs. So when no products are produced, the costs are 1,000, and that corresponds to our fixed costs. Now to get an idea of what our variable costs are, let's go ahead and find C of 10 and C of 11. So C of 10 means I need to put 10 into the function. So 5 times 10 plus 1,000 is 1,050. C of 11 is 5 times 11 plus 1,000, that's 1,055. That means increasing our production from 10 to 11, our costs change by C of 11 minus C of 10, which is 1,055 minus 1,050, or 5. So this is telling me if I increase my production by 1 unit, my costs change by $5. So the 5 that we see up here has something to do with our variable costs. And in fact, what we're seeing now is when we increase our production by 1, that 5 is telling me how much my costs increase by. So the 11th item cost us $5. This is just the slope of the linear cost function, and that means our slope is the cost per item. So we see that there are really two terms here. The constant term here is our fixed cost term. The 5x, because it has an x in it, and as we make x bigger, this amount is going to change. That's our variable cost term. Now let's expand on this a little bit Before we looked at C11 minus C of 10. Well, what if we took C of x plus 1 minus C of x? So whatever your production level is at x, we're going to subtract that from 1 more than that. So C of x plus 1 means we put x plus 1 into our cost function. So 5 times the quantity x plus 1 plus 1,000. And C of x was just 5x plus 1,000. When I subtract these, I need to remember to go ahead and distribute my minus. And that leaves me with 5x plus 5 plus 1,000 minus 5x minus 1,000. If I simplify, I'm just left with 5. So we went from C of 11 to C of 10. Our cost increased by 5. This is telling me if I increase my production 1 unit, no matter what we were producing, it's still going to be an increase of 5. Economists define this rate of change of the cost function, or the slope of the cost function, as the marginal cost. Graphically, the marginal cost at a level of x is the slope of the cost function at x. In our case, we just saw that the slope of the cost function was 5, and since it was a straight line, it never changes. If we were to have a cost function that wasn't a straight line, that maybe was curved, well, then our marginal cost would change because our slopes change as we increase or decrease production. Like we said, for a linear function, the marginal cost is equal to slope. And so now let's take a look at a picture of a cost function that is not a straight line. I have a blue graph here that represents my cost function. I have a pink line on here that is simply a secant line through 2 points on that cost function, and it's at a point x and 1 bigger than that. And I've also put on here my tangent line, the line that just grazes there. What we want to do is to be able to look at those things and see if we can make some connections between the cost function, the secant line, and the tangent line. So let's go ahead and look at the secant line and the cost function first. So what we were just working out a moment ago was C of x plus 1 minus C of x, and what we said that was the difference in cost between a production level and 1 more than that. And so basically what I'm seeing on here is a secant line goes through those 2 points, and if I were to go ahead and find the slope of this secant line, its rise would be C of x plus 1 minus C of x, the difference between the 2 y values over here, and my run, well, that'd just be 1, because the difference between x and x plus 1 is only 1. The slope of the tangent line, on the other hand, well, we can go ahead and put this slope on here, and what we're going to notice is that the derivative tells us the slope of the tangent line. So c prime of x is the slope of the tangent line. How are these two things connected? Well, if we go ahead and try and put on a slope, we can think of this as c prime of x over 1. So that means that the rise is the derivative of the function and the run is 1. So comparing those things all together, what I'll notice is on the tangent line, the slope is c prime of x over 1. On the secant line, the slope is c of x plus 1 minus c of x over 1. And if these points are close enough together, usually the rise corresponding to the tangent line and the rise corresponding to the secant line are really close to each other. So that means that the increase in cost that I get is usually going to be very, very close to the derivative at that point. The actual costs of increasing our production is just the slope of the secant line. An approximation of that is the derivative. And a lot of the time, it's going to be easier to compute the derivative than it is to do c of x plus 1 minus c of x. So if we have our c of x, the slope of this function is 5, and to understand what this means, we need to notice that the independent variable has units of production on the x, and on the dependent variable, it's dollars. Since we're computing a slope, the units are going to be the units of the rise, which is dollars, over the units of run, which is production. So we're going to get $5 per unit of production. This means that when we increase the production by 1 unit, our costs are also going to increase by $5. In other words, the marginal cost is simply the cost to increase the production by 1 unit, approximately. The only time that this is exact is when we have a linear function like this. Any other particular curve, the actual cost to increase the production and the marginal cost are very, very close to each other. If you're asked to compute the actual cost of increasing the production, you'll need to do c of x plus 1 minus c of x. If you're asked to approximate it, well, then you can just use the derivative. To analyze a business, we're going to use that cost function c of x along with our 2 other functions. Revenue, remember revenue is r of x, and it tells us how much money is coming in at a particular number of units sold, and it's describing the money that you receive from the sale of those products. P of x is the profit at x units sold, and that's just the difference between my revenue and my cost. If I have more revenue than cost, I'm making money. If I have more cost than revenue, well, then I'm losing money. Now the revenue, to come up with that function, the revenue from selling x units is simply the product of the price per unit P. Notice that I'm using little p here because capital P is the profit. This P has to do with the prices per unit and the number of units x sold. So R of x is simply P times x. A lot of the time that P is just a constant, and then we take the constant times x. Sometimes the P is given in terms of a demand function, and it'll be a formula. Notice that this function is a function of x. Also, be careful in using R of x, because in some problems, x or R of x may be defined in multiples like hundreds of units or thousands of dollars. So when you try and interpret the revenue, you need to take those things into account. Now our profit function capital P of x is just the difference between the revenue function and the cost function. So if I know capital R of x and capital C of x, if I subtract them, that'll give me my profit function capital P of x. Be careful again to distinguish between the little p, which is our price per unit, and capital P, which is our profit function. Now let's try and do an example involving these things, and let's see what we get when we work out all these things and try and interpret them. So the total cost in hundreds of dollars to produce X thousand barrels of a solvent is given by the cost function 2x squared plus 50x plus 1,000. I want you to find the marginal cost to produce 10,000 and 30,000 barrels of solvent. So since I'm asking you to do the marginal cost, we're going to be computing the derivative of this function. C prime of x is going to be the derivative with respect to x of 2x squared plus 50x plus 1,000. This is a sum of 3 terms, so we can go ahead and take the derivative of each one of these 3 terms and then add them all together. So the derivative of 2x squared is going to be the derivative of x squared, which is 2x, times the 2, which gives me 4x. The derivative of 50x is going to be the derivative of x, which is 1, times 50, which gives me 50, and 1,000 is a constant, so when I take its derivative, it's going to be 0. C prime of x, the derivative of the cost function, is 4x plus 50. Now what I need to do is I need to figure out the marginal cost to produce 10,000 barrels of solvent, but remember x was in thousands of barrels, so I need to take C prime and put 10 into it, not 10,000. And when I do that, I get 4 times 10 plus 50, which is 90. That means that the marginal cost of producing 10,000 barrels is $9,000. Remember, the output was in hundreds of dollars. So $9,000 is 9,000. So this means that producing 1,000 barrels more, 1 unit, and the units here are thousands of barrels, will be approximately $9,000. Now the actual cost of producing that extra 1,000 barrels, to find that, I would have to go ahead and do C of 11 minus C of 10. That would be 11 into my cost function, which gives me $1,792. 10 into my cost function gives me $1,700. When I subtract those, I get 92. And that 92 corresponds to $9,200. So the actual cost is $9,200. The marginal cost was $9,000 because remember, in this case, because this is a curved function, the marginal cost is an approximation of the actual cost of increasing our production by 1 unit. If we go ahead and now find the marginal cost at 30,000 barrels of solvent, well then we need to put 30 into our cost function. That gives us 4 times 30 plus 50, or 170. The actual cost of producing an extra 1,000 barrels at that level would be C of 31 minus C of 30. That would be 4472 minus 4300, or 172. So these values come pretty close because the marginal cost was 170. The actual cost of producing an extra 1,000 was 172.